What is
Oh,
intelligence, really? I mean, we
uh-huh.
interact with AI systems every single day, and they seem incredibly smart.
Right. Almost magical sometimes.
Exactly. They write for us, they create art, answer these really complex questions. But uh, are these systems truly intelligent? Or are we maybe, confusing their impressive capabilities with something deeper, like genuine evolving intelligence?
That's a crucial distinction, and it's precisely what we're diving into today.
Okay.
Our source material is built around Professor Yuma's really powerful keynote, Pursuing the Nature of Intelligence. And this isn't just about looking at what current AI can do.
Right.
It's much more a critical evaluation, looking at its fundamental principles, its inherent limitations, and maybe what true intelligence might actually look like. And he draws these profound lessons directly from nature's own blueprints.
Okay, so our mission today is really to unpack Professor Ma's bold claim.
Yeah,
And it is pretty challenging, isn't it?
it definitely is.
He says, any system without mechanisms for self-correcting and self-improving its existing knowledge, however large, does not have any intelligence. So we're going to critically examine how this statement kind of fundamentally redefines our whole pursuit of AI
Yeah, pushing us beyond just bigger and bigger models.
towards truly smarter systems.
Right.
So to really get this Professor Ma's argument, we kind of need to rewind, like way back.
Not just to the start of AI.
No, like to the dawn of life itself.
Yeah.
What can nature teach us about intelligence from, its earliest blueprints?
Well, Professor Ma argues that intelligence isn't just some arbitrary thing. It evolved as life's ultimate survival mechanism.
Okay.
Think about it. The universe is constantly tending towards disorder, right? Increasing entropy, as Vaclav Havel observed.
Right, that tendency towards chaos.
Exactly. Well, life's constant struggle against that disorder, its incredible ability to acquire knowledge and predict the world around it. Ma says that is intelligence at work.
Wow. So intelligence is life fighting entropy.
In a fundamental way, yes. It's a pretty profound idea when you just consider the sheer length of time life's been on Earth.
Billions of years.
Truly. And if we look at that grand timeline of evolution, intelligence isn't just a human thing, not at all. It's interwoven with life itself. The very first DNA, it appeared about, 4 billion years ago?
Incredible.
And Professor Ma compellingly describes these early DNAs as pre-trained large models.
Huh. Okay. Nature's original LLMs.
Sort of. Imagine nature's earliest trial and error learning. It's like a simplified version of reinforcement learning. Those random mutations that happened to lead to survival got rewarded. They continued to exist.
And the ones that didn't.
They just faded away. It's intelligence learning from success and failure, but on this, cosmic scale.
It's fascinating how much patience was involved in nature's approach, though. So, okay, the last universal common ancestor, LECA, that emerged around 3.5 billion years ago. But then it took another 3 billion years for the first braid to show up, and a tiny nematode around 550 million years ago.
A huge gap.
Yeah. And this wasn't just some biological curiosity, was it? It was a monumental leap. It enabled individual learning, feedback.
And that then fueled this explosion of lives in the Cambrian period, just 50 million years later?
Wow. So the brain was the catalyst.
It really shows how critical new forms of intelligence are for rapid adaptation and diversification. That rapid explosion of lives after the brain emerged, it directly emphasizes how these new mechanisms like individual memory, learning from feedback, led to this unprecedented rate of evolution.
Okay, so it highlights a key distinction then.
Exactly.
So if nature builds this sort of species-level wisdom through DNA, what Professor Ma calls phylogenetic intelligence.
Right. Inherited intelligence.
How does an individual animal learn, during its own lifetime?
Okay, that's where ontogenetic intelligence comes in. This is the intelligence developed by an individual creature. It's through its personal memory, perception, continuous feedback, and, this is crucial, error correction.
So learning from mistakes.
Constantly. Professor Ma highlights that every animal, in a way, is like a mini Newton, always learning an accurate world model through its experiences, refining its understanding of gravity, prey, predators, its environment, moment by moment.
And this whole evolutionary thread, it just continues right into human history, doesn't it? Leading us eventually to this ambition for machine intelligence.
It's a clear continuum.
Yeah, you go from Neanderthals developing tools like 310,000 years ago to societal languages maybe 70,000 years ago, written knowledge around 3500 BC, the scientific renaissance, and then boom, the explicit ambition of machine intelligence. really kicks off in the 1940s.
Each stage building on the last, acquiring and predicting more effectively.
Exactly.
And that ambition for machine intelligence starting in the 1940s, that was truly a magic era in its early days. You had these visionaries, right? Norbert Wiener with cybernetics, the study of control and communication in, well, living things and machines.
Right, feedback loops.
Precisely. Then McCulloch and Pitts with their early artificial neural networks, Claude Shannon and information theory, John von Neumann with game theory, Alan Turing, the Turing machine, the Turing test, they laid the groundwork.
And their goal was pretty clear then.
Yeah, and very biologically inspired to imitate animal intelligence. That meant systems that could perceive so, encode information, predict, decode it, and critically learn memory from experience.
And early AI was, directly inspired by biology. That makes total sense. You had scientists like Golgi and Cajal giving us this foundational understanding of biological neurons. And later, Hubel and Wiesel's groundbreaking work on the visual cortex, that directly influenced concepts like convolutional neural networks, CNNs.
We were literally trying to reverse engineer nature's best learning systems. But here's where the critical evaluation of modern AI really bites.
Okay.
Despite these biological inspirations, a huge challenge with a lot of today's AI, especially these deep neural networks, is what Professor Ma calls the black box problem.
The black box.
Yeah. These systems are often empirically designed, built through massive trial and error. He even suggests it's almost like alchemy. We throw vast amounts of data at them, they get incredibly good at certain tasks, but...
I don't know how they do it.
Exactly. Their internal workings remain opaque, hidden, black boxes.
And you mentioned the consequences. Difficult to explain, impossible to guarantee, and costly to improve. Can you give us some examples? Where does this black box problem really hurt us in the real world?
Oh, absolutely. Think about, say, an AI recommending a critical medical treatment.
Okay, high stakes.
Very high stakes. Or making a split-second decision in a self-driving car. Or even just influencing a major financial transaction.
Wow.
If we don't understand why it made that specific choice, that specific recommendation, how can we truly trust it?
Right, if it fails.
If it fails, and we often don't know how to reliably fix it, or even how to prevent the same error from happening again under slightly different conditions. It's like, imagine having a brilliant chef whose recipes are a complete secret. They make amazing food most of the time. But if a dish goes wrong, you have absolutely no idea why. You can't fix it reliably. You can't even replicate the successes consistently. You're just constantly experimenting, tweaking, not really engineering.
That's a great analogy. So it's tinkering, not understanding.
Pretty much. So instead of this alchemy, Professor Ma argues it's high time to develop a principled approach. We need to move towards white box models.
See inside the box.
Exactly. Systems where the internal logic is transparent, understandable, where we know why they do what they do. And to get there, he proposes these three fundamental questions that any truly intelligent system has to answer. What to learn, how to learn, and why correct.
Okay, 3 pillars. Let's start with the first one. What should an intelligent system actually be learning?
Right. Ma posits that intelligence exists, basically, because the world is not entirely random yet, and it is still largely predictable.
Okay, so predictability is key.
He argues it's the only inductive bias necessary. You don't need to hardwire tons of complex human design rules into an AI. The world itself, with its inherent regularities, provides the fundamental structure needed for learning.
And mathematically, this predictability shows up as, you called it low dimensionality.
Yeah, exactly. Think of it like this. You have this huge, messy, high-dimensional data set, millions of points. Low dimensionality means that even within all that seeming chaos, the important stuff, the predictable patterns, they actually lie along much simpler hidden structures, like finding a single, simple path through a dense forest.
Okay, give me an example.
Sure, weather forecasting. We can predict tomorrow's temperature or rainfall, roughly anyway, because weather patterns, despite their complexity, follow underlying predictable dynamics. They're not totally random.
For gravity.
Or gravity, a falling object's acceleration is constant, predictable. That's a low-dimensional rule governing a physical system.
And this low dimensionality, it enables some powerful abilities.
Definitely. It allows for completion, like how GPT predicts the next word, or how a system fills in missing parts of a picture. It enables denoising, recovering clean signals from messy data, like getting a sharp brain MRI from a noisy scan.
Cleaning things up.
Exactly. And crucially, it supports error correction, which leads to robust recognition, like recognizing a face even if it's partially hidden or the lighting is bad. The system finds that underlying low-dimensional face structure despite the noise.
Okay, so that's what to learn. Find the predictable low-dimensional structure. Now, the second principle. How to learn.
Professor Ma proposes a unifying principle here. Compress to reduce entropy of the observed, noisy data distribution.
Compress. Reduce entropy. Okay, unpack that a bit.
So learning is fundamentally about identifying and distilling these low-dimensional structures we just talked about. It's about making the information more compact, more organized, less random, less entropic.
Like finding the essence of the data.
Precisely. And the mechanism for this compression, often it's through denoising. Think about diffusion things, spreading out, getting messier, entropy increasing.
Right.
Well, the inverse process, denoising, does the opposite. It actively decreases entropy. It cleans up the noisy data, revealing that underlying structure. He argues this is a fundamental learning mechanism. It's kind of like how our brains filter out irrelevant noise to focus on the important signals.
And this is where even things like deep neural networks come in.
Yeah.
Because they often seem like black box magic.
Exactly. What's fascinating is that even complex DNNs, like the transformers in today's big AI models, can be interpreted as actually doing this compression. They are essentially iterative operators, maybe like gradient descent, finding that core low-dimensional structure in massive amounts of data.
So it's not alchemy after all.
Well, the argument is we can move away from the alchemy. We can see these layers as principled steps performing compression and sparsification. This allows for, potentially, better semantic interpretability, as he mentions with models like Crate. It lets us design better networks from first principles, explainable, scalable, efficient architectures, without just endless trial and error.
Okay, that's a big shift. What to learn, how to learn. Which brings us to the third critical question. Why?
Correct.
This principle is achieved through something called bidirectional encoding and decoding, basically auto-encoding.
Okay, what does that mean?
It means the system can both compress information into a concise representation that's encoding and then regenerate it, or something close to it, back from that representation that's decoding. But the real kicker here is closed-loop feedback.
This sounds like cybernetics again. Wiener's idea.
You got it. The system learns by constantly sensing, acting, and then checking its actions or predictions against reality.
Like learning on the fly. Exactly. In nature, intelligent systems don't just learn once and then stop. They learn from continuous closed-loop feedback. The encoder acts like a sensor, perceiving the world. The decoder acts like a generator or a controller, producing actions or predictions based on the internal model.
And they talk to each other.
Constantly. They engage in what Ma calls a self-critiquing game. The system is always checking its internal world model against what actually happens, making corrections. It's not just about piling up data, it's about continuously validating and refining its understanding.
And this self-consistency, this self-critique is vital
Because it prevents catastrophic forgetting. This is a huge headache in traditional AI.
Right, where learning something new makes it forget the old stuff.
Exactly. This continuous feedback loop, this self-correction, is what enables truly autonomous incremental learning, just like biological systems. It allows them to adapt to a constantly changing world without just overwriting task lessons.
Okay, so we've got the three pillars. Learn what's predictable, parsimony. Learn by compressing, compression. And learn by self-correcting, consistency.
And if we look back at nature, as Ma constantly urges, we see these exact mechanisms everywhere. Sparse coding in our visual cortex, how our brains efficiently represent what we see. Subspace, embedding how we group similar concepts together. Predictive coding, how our brains constantly predict what sensory input is coming next and update based on errors.
Nature figured this out billions of years ago.
Pretty much. Nature's blueprint has been running on these principles for eons.
So Professor Ma's vision for, let's call it AI 2.0, it builds directly on this.
Directly. He envisions AI implemented not as these single giant black boxes, but as massive parallel distributed hierarchical systems of these autoencoders. Think of something analogous to the cortical columns in our brains.
Wow.
The basic unit for autonomous learning would be what he calls closed-loop transcription, and the unified goal across the whole system, maximize information gain, always be learning, always improving the model.
Building systems that are inherently curious and self-improving.
That's the idea. And this leads us straight to Professor Ma's really critical redefinition of intelligence itself.
Okay, hit me with it.
He defines an intelligent system as one that has the mechanisms for self-correcting and self-improving its existing knowledge or information.
Self-correcting and self-improving.
And here's the direct critique, the part that really challenges current AI thinking. Any system without such mechanisms, however large, does not have any intelligence.
Whoa, okay, that's a mic drop moment, however large. So even the biggest LLMs today.
By this definition, they might fall short. Think about it. Ma flips our common understanding. It's not just how much a system knows, like the size of its training data, it's knowledge.
Right, the giant library analogy.
Exactly. True intelligence, he argues, is the speed at which that library can rewrite itself, update itself, improve itself. It's the rate of change of knowledge. Intelligence equals DDT, knowledge, the derivative.
So intelligence isn't the volume, it's the acceleration of learning.
Or at least the velocity, the rate of improvement. That's a profound shift, isn't it?
It really is. So current LLMs like GPT-4, while they know an incredible amount, they lack that autonomous self-improvement loop. They need humans to retrain them, fine-tune them.
Fundamentally, yes. They don't inherently possess that internal self-critiquing game or that continuous closed-loop feedback that drives genuine, ongoing learning and adaptation in biological systems, according to this view. Knowledge is the accumulated understanding, like an integral over time. But intelligence, Ma asserts, is the rate of that accumulation. It's about the ability to learn and adapt, not just the sheer size of the data set it was trained on.
Okay, so this redefinition, it also sets a much higher bar for how we even test for true intelligence, doesn't it?
Absolutely. Forget just regurgitating facts from training data. Ma proposes new scientific tests. Beyond mere memorization, true intelligence, by his definition, needs to be certified by increasingly complex capabilities.
Like what?
First, the Wiener test. This measures the ability to self-learn. Think animal intelligence, autonomous adaptation learning effectively without explicit programming for every single scenario.
Learning on its own. Okay.
Then there's the familiar Turing test, but maybe interpreted more deeply. The ability to understand in human-machine interaction. Moving beyond just clever pattern matching to really grasp intent, context, meaning.
Understanding, not just mimicking.
Right. But then he goes even further, proposing the Popper test. This is about the ability to theorize.
Theorize.
Like a scientist.
Exactly. Can an AI generate and then verify new scientific hypotheses? Can it actually contribute to advancing fundamental understanding, not just applying knowledge we already gave it or predicting the next token?
Wow, that's a whole different level.
It is. These tests represent a critical differentiation. They separate truly advanced pattern recognition and prediction from what Professor Ma defines as genuine, self-improving adaptive intelligence. What an illuminating deep dive this has been. Seriously.
Yeah.
We've critically examined Professor Yi Ma's really compelling vision for intelligence, moving us, hopefully, from this era of empirical black box AI.
The alchemy.
The alchemy, yeah, towards a more principled white box approach, driven by these core ideas: parsimony, knowing what to learn; compression, how to learn it efficiently; and self-consistency, why and how to correct itself.
And we've seen how true intelligence, by this quite demanding definition, lies not just in what a system knows, but really in its capacity for continuous, autonomous self-correction and self-improvement.
Mirroring nature's most effective learning strategies, honed over billions of years.
Exactly.
So here's a final thought for you, the listener. As you interact with the increasingly sophisticated AI in your daily life, search engines answering questions, creative tools generating text and images.
Which are everywhere now.
Everywhere. Ask yourself this: does that system truly understand what it's doing? Or is it demonstrating incredibly advanced, maybe even mind-boggling, pattern recognition and prediction based on just astronomical amounts of data?
What would it really take for an AI to genuinely learn, correct, and improve its own understanding, its own internal model of the world, without us constantly intervening?
And maybe the even bigger question: if AI does achieve this level of intelligence, this ability Professor Ma describes, not just to know things, but to actively increase its own rate of learning, what are the implications then?
Yeah, the profound implications for our society, for science itself, and maybe even for the future nature of human progress. Lots to think about.